Bubbles in water are a common phenomenon, but making them much smaller gives them a totally different, astonishing new power. These bubbles are called microbubbles. They have a diameter of less than 0.05 of a millimeter. That's less than half the width of a human hair. Throughout Japan, we're starting to see the introduction of innovative ways to use these microbubbles for efficient purification of water. In this video, we'll take a look at the cutting edge of microbubble technology. This is a reservoir in a town in the mountains of Fukuoka Prefecture in western Japan. Water from here is sent to a purification plant, and from there it's supplied to the town. In the middle of the reservoir is a microbubble generator. The microbubbles prevent the growth of a problematic phytoplankton called blue-green algae. Blue-green algae grows in ponds, lakes and other still bodies of water at warm times of year. It causes a lack of oxygen in water near the bottom, so the water becomes stale and gives off an unpleasant smell. At the purification plant, filtration is used to purify the water from the reservoir. Without microbubbles, blue-green algae in the water could prevent this process. Here's a model of the filter. The water is passed through sand and gravel for 6 hours. Chlorine is then added to the water to make it fit for household use. Any blue-green algae in the water sticks to the sand on the surface and creates a film, preventing water from passing through. Normally, the sand on the surface is replaced monthly, but once blue-green algae has started to grow, the sand needs to be replaced every 3 days. 3 months after the introduction of the microbubble system, the blue-green algae had almost completely disappeared, enabling a stable supply of clean water to the town. The microbubble generator draws up water from the bottom of the reservoir, adds microbubbles to it, then pumps it out in 6 directions. This process infuses the water in the whole reservoir with a sufficient amount of air and causes the water to circulate, thereby preventing the growth of blue-green algae. So what are microbubbles? To find out, we visited this laboratory, which is conducting research on microbubbles. Let's see how microbubbles form. At first, large bubbles are created. Then we see a white area which consists of microbubbles. Let's see what happens if the generator is stopped. 30 seconds later, the microbubbles are slowly rising to the surface and we can see clear water forming at the bottom of the tank. A minute later, the microbubbles are still gradually rising toward the surface. One feature of microbubbles is that they rise very slowly. In the space of 1 minute, microbubbles with a diameter of 0.01 of a millimeter rise only 3 millimeters. The larger bubbles that normally form in water quickly rise to the surface and burst as seen here. Microbubbles move very slowly in comparison. Reservoir, the microbubbles are carried along with circulating water, carrying air to all parts of the reservoir. This device draws in air and water and uses a vortex to mix them, creating microbubbles. Air that has been mixed using the vortex still comprises large bubbles at the center of the nozzle. As this swirling current emerges into water where there's no flow, the movement of the vortex is abruptly halted. Here, the force of the vortex is converted into a force that can finally break up the air bubbles in the water. As the air bubbles are broken up by this force, they form microbubbles. Let's look at the movement of the bubbles as they leave the nozzle. When the generator has just started up, we can see the vortex that's formed at the nozzle. Bubbles emitted at this stage are still large. As the vortex speeds up, it can no longer be distinguished. At this point, white microbubbles are formed as the vortex coming out of the nozzle encounters the still water and its force is changed into one that breaks bubbles apart. Japanese research into microbubbles has been publicized by the scientists, and it's attracting great interest from companies and universities in Japan and overseas. In Higashi Matsushima City on the coast of eastern Japan, a seafood company uses microbubbles to clean oysters. The oysters are kept in a water tank for a whole day before being shipped. The tank gets dirt out of the oysters and kills bacteria to prevent food poisoning. Microbubbles are pumped into the tank. To make their cleaning effect even greater, small amounts of ozone are added to the air. 3 hours after the start of microbubble generation, the dirt out of the oysters has risen to the surface of the water. How clean are the insides of the oysters? This is an oyster that has been kept in a conventional water tank. Let's make a comparison. The inside of an oyster from the tank with microbubbles is much cleaner and whiter. This shows that the microbubbles have removed all the dirt. An important property of microbubbles is that they have an electric charge and thus adhere to impurities. These images were taken using a special camera. The two bright points are microbubbles. The large solid mass is a piece of clay. The microbubbles have stuck to the clay and are slowly carrying it up to the surface. It's by this process that microbubbles removed the dirt from the oyster we saw earlier. Some food processing plants have adopted this technology in the treatment of wastewater. This plant makes processed food items using minced fish. It emits 200 to 300 tons of wastewater each day. The wastewater contains a large amount of oil, so treating it used to be extremely expensive. The most common way to treat wastewater is the activated sludge method. Microorganisms in the tank clean the water by breaking down the organic matter that it contains. But microorganisms can't digest matter in wastewater containing oil, so this food processing plant originally treated its wastewater using chemicals. An unwanted result was a large amount of sludge that could not be broken down and had to be disposed of as industrial waste. The plant used to produce more than 300 tons of sludge per year. But since it started using microbubbles, it has seen this amount decrease to just 5 or 6 tons per year. The reduction in sludge has meant savings of about $57,000 per year on chemicals and sludge disposal. Microbubbles have another property that can be used in wastewater treatment. As they slowly rise through the water, they collapse and disappear. These images from a special camera show the process taking place. The microbubbles are the round black points. After about 10 seconds, the microbubbles become smaller under the pressure of the water around them. Then they collapse and disappear altogether. Let's take another look. The microbubbles release energy at the moment when they collapse, and this energy breaks down the organic matter that's contaminating the water. If If ozone is used to create the microbubbles, even more energy is released. This is the wastewater treatment room at the food processing plant. How are microbubbles used here? Wastewater from the plant is first stored in an underground tank. It contains a lot of oil and is too dirty to be cleaned using microorganisms. From the underground tank, it's pumped up to a large tank for primary treatment. In the primary treatment tank, ozone microbubbles are used to clean the water for 30 to 60 minutes. The contamination floating on the surface of the water is sludge, which can't be broken down. How clean does the wastewater become during the decomposition process? If we compare it with untreated wastewater, the difference is clear. The wastewater then flows to the secondary treatment process, which takes place in 3 cylindrical tanks. In these 2-meter-high tanks, the water is cleaned further using ozone microbubbles. The water has ozone microbubbles blown through it for 15 minutes in each of the 3 cylindrical tanks in sequence. Even in the first of the secondary treatment tanks, the water is much cleaner than it was in the large primary treatment tank. Even more of the contamination is removed in the second and third tanks. This clean water is the final result. These are samples of the wastewater after each stage of treatment, with untreated water on the left and the finally discharged water on the right. At each stage, the substances comprising the contamination have been broken down into water and carbon dioxide. The finally discharged water is extremely clear. It's almost as clean as household tap water, far exceeding wastewater standards. Microbubbles are also being used in the Onga River in northern Kyushu. This water is the source of the municipal water supply. The mouth of the river has a 400-meter wide, 4-meter deep estuary weir across it. Blue-green algae used to grow here, and local residents complained that their tap water smelled moldy. Microbubble generators were installed as a countermeasure. There are 6 microbubble generators in all, 3 on each bank at 200-meter intervals. Water from the bottom of the river is pumped up and mixed with microbubbles, creating circulation in water that would otherwise be still. Blue-green algae has almost completely disappeared from the river, and there have been no more complaints about the smell of the municipal water supply. Microbubble technology was developed in Japan, and following extensive testing and refinement, it's delivering great benefits in various river and lake environments. It can now even be used to treat wastewater from chemical plants, which contain substances that are extremely difficult to break down. At the technological cutting edge of efforts to improve aquatic environments, microbubbles are the key to clean water and a more environmentally friendly way of life.